Is everyone back in that's going to come in? All right, let's get started. Hey, everybody. My name is Cliff. I am from a company called Boundary, and we do a type of network monitoring as a service. So we'll give a pitch later on. This is more thought leading. By the way, that's all just ironic. Everyone knows that, right? I think Dr. Gunther got the wrong idea. Okay, so my whole point in being here today, I want to tell you guys a little bit about at least how I think about the monitoring problem, the types of things that we're going to be doing at Boundary, and hopefully get you inspired. And it's a lot of overlap with previous talks, so that's good. So anyway, this is kind of the way that I like to think about the monitoring problem, right? So I kind of like to think about it as sort of a hierarchy of needs. Where first is the orientation, like it's just another way of looking at the OODA loop. But like, what is going on? What is my situational awareness? Like, how do we're throwing out terms again. But what is going on? How do I know what my machines are even doing? What my services are doing? How do I know what experience I'm giving to customers? Because by default we don't even have that. And then the determination, is something wrong, right? So. First of all, what is wrong? Second of all, is something wrong? And thirdly, why is it wrong? Why? What is the root cause or the contributing causes, I should say, to any individual issue that we might find? And then, of course, there's what do I do about it? So we're actually not going to get to the fourth one today, mainly because I haven't thought too much about it. But except when I solve my own problems, right? But anyway, so the way that traditionally we climb this hierarchy, because this is actually a really hard problem, right? We're talking about general cognition here, essentially, with a set of inputs that are extremely low bandwidth compared to the sensory apparatus that we're given by nature, right? Yeah, everyone agrees with that? This is perception? Yes, okay, good. That makes it easier. Yeah, so how do we climb the hierarchy? Essentially, in order to deal with the low bandwidth inputs that we get from our machines, we have to make simplifying assumptions. Basically, we make simplifying assumptions about what might be going on, and then eventually those assumptions start to break, right? So we see that very clearly with the whole monitoring sucks meme, right? Which mainly seems to be just a jab at Nagios, from what I can tell. Everybody's whipping boy today. It's easy to throw that under the bus. But the simplifying assumption of Nagios was that that things are static, right? Not only thresholds are static, we'll get to that in a moment, but that the shape of your stuff is static, right? Your deployed environment, you're deploying to a data center that's not going to be, getting servers anytime soon, right? Like, you're not going to be deploying new code, How many times do you do it, John? Twice a minute? Yeah, something. You're going to have a bad time. No, it's but no, you're not deploying code continuously, as they say. You're not doing any of those things. It's not built for that kind of, highly dynamic, environment. Because that's a simplifying assumption. Dealing with those things is hard. It's hard both computationally, and it's difficult from a, from a mental model standpoint as well. So we're left with, the state of the art here is, we have this zoo of homegrown stuff that we eventually meld together, and this is where actually Jason and I diverge very greatly in our opinions. He's very much for the whole cobble together a thing out of other things. I think that that's actually the wrong model. But hey, we'll see who's right eventually. So basically it's either the zoo of homegrown stuff that doesn't quite work together, and none of them really understand each other, and you are left. We'll show you what you're left with in a bit, and you'll know. But I mean, and then you have the commercial point solutions, right? So you have the essentially the crack the brain open things like New Relic, and New Relic is crack the SQL query open. But then you have the app dynamics and so forth that do the bytecode instrumentations, like crack the VM open, what's going on. But again, it's not the big picture. It's just vivisection, right? So it's a very very point. Like many successful commercial things, it's very focused and pointed at one particular problem. And then, of course, we have, which is actually, many of you people don't even, like, people who go straight into web engineering, who've never, done a tour of duty in, the old school enterprise, don't even know these things exist, which I think is amazing. But, I mean, there's, all these the monitoring industry has been around since there's been computers, right? And like there's stuff out there that exists, and I didn't even know about this until I decided to start a monitoring company, which is a whole different thing. But anyway, there's like all this stuff out there. BSM companies is what they're called for the most part, that try to integrate in many different systems into one kind of thing to make a pane of glass you put in the knock. And by the way, there's a whole services org you got to pay into to man years of configuration work that goes into it, and custom this and that. And it's basically shelfware essentially. By the time it's done, it's out of date. So how do we climb this hierarchy of monitoring needs? And this is how traditionally we have done it, right? So in the beginning we have metrics, instrument a thing, put it somewhere, graph it, the analysis happens here in the head, right? And so essentially what we end up with when we let these things grow organically and when we sort of stack a bunch of stuff together is we end up with a gigantic stack of R&D tools, which we then put our finger onto one and then we scroll up and down in order to see whether the correlation exists. Right? We have a name for that. We call it the all-spa method. Right? And it leads to greasy screens. No offense. Right. So that's the way that we've traditionally done it, and this is. I mean, it's similar to the way that Boundary works now. Right? We collect a bunch of stuff. We have a high-volume pipeline that chews through a bunch of metrics, but essentially, like theoretically, it's like very, very similar in idea. You take a bunch of metrics in, you put them onto a time plot, you try to correlate them together, and then you tell yourself a story in your head about what might be going on based upon these pictures. Hopefully that story is going to tell you whether something is wrong. And then we get to the point where we say, okay, I don't want to stare at these graphs all day. I don't want to put my finger on the screen. Just what do the lines mean anyway? And I think we've been over this today, right? Like, what is this graph even trying to tell me? And so we come to alerts, which is the way that the system has of telling you when something is wrong. The problem here, so it's very interesting because we focused earlier on the human aspect of things. I'm going to focus more on what can the machine do to augment the human the human aspects. But alerting is interesting because really it's a classification problem, right? So you have some sort of data input, right? You want to put it through some sort of a thing, a model, a filter, whatever, you want to do some sort of transformation on it, and you want to be able to classify it into a number of different buckets, right? And so you can call them priority levels, you can call them whatever, but the idea here is that for any given set of inputs, you want to be able to say, is this bad or good, or is this varying gradations of bad or good, right? Maybe even give it a score if you're feeling jaunty. But basically, we think about classification models, and I'm no machine learning expert, so don't ask me for the nitty-gritty math of many of these things. I know enough to be dangerous, but certainly not enough to assert any sort of special knowledge. But I mean, classification models are actually a pretty well-studied art form. Most of the literature and most of the stuff out there is really oriented about text classification, since selling ads is a thing that a lot of people want to do. But we can sort of see here where we are in terms of a classification algorithm for alerting, right? Like our alertings, most of the most basic alerting systems are static thresholds. Really simple, doesn't need to be explained. Then we have seasonal predictive stuff. You have Holt Winters. You can calculate EWMAs against time buckets. There's all sorts of interesting things you can do there to kind of solve your problem, right? Of, hey, on the weekends, less stuff happens. At this time of the day, less stuff happens. Tell me about that. Tell me things are okay when less things are happening. And then there's again a lot of Dr. Gunther's work, capacity predictive stuff like the universal scalability law. Things trying to say, like, here is the size of this machine in terms of work units, and how many work units can we actually put in here, and when we deviate from the expected amount of throughput, what does that tell us about what's going on with the machine itself or the software that's on it? And then we get into the magical stuff, which I just think it's funny because, I hear a lot of people talk about this, and we've even talked about this at some point internally at Boundary, and a lot of these discussions end up everyone sort of dances around the idea. And it's like, oh, we'll just sprinkle some machine learning on it and it'll be fine, right? Like, these are actual, like, there's math involved. You're going to need to read some PDFs. It's fine. You'll get used to it. But there's actually some really interesting things here. SVM. I'm not going to go into the real nitty-gritties of these things. There's lots of, like I said, PDFs with formulas that you should read. But SVMs are very interesting because I think with that Tukey plot, the big clouds of stuff. SVMs are actually that's what they're meant to detect, right? If you have point clouds in an n-dimensional space with big gaps between them, the SVM is the support vector model is supposed to draw a plane through that n-dimensional space. And then that plane is how you bucketize the classification of things, which is really cool because you can make a machine do that. And you don't have to stare at an n-dimensional thing and get all Tom Cruise and Minority Report on it and all that shit. So that's cool. Neural networks are an interesting thing. I find with great interest many of the people moving to Google these days to work on those sorts of things. Turns out they're actually useful, which was not true for a while. But for things like pattern recognition. And I mean basically perception, right? So like, and the interesting thing is like mathematically, like things like SVMs and a lot of these, a lot of them are like almost isomorphic, right? Like a perceptron is just a really simple SVM, which is also a neuron. Yeah, it's kind of cool, but kind of mind blowing as well. Yeah. So that's cool, but like a lot of those things, just assume that I'm plotting one metric into some sort of n-dimensional space and saying, hey, what the hell should I even alert on, right? And what's what Matthias was saying, the soul metric, right? Like why, like what do I even do here? And turns out in the monitoring world, or in the commercial monitoring world, like the one thing that everybody kind of harps on, because that's what gets checks written at the end of the day, is end user response time, or end user some form of end user a proxy for the user experience, right? Because that's what's actually driving your business. Are your users happy, right? Are their CI jobs completing? Are they able to buy handcrafted things? So on and so forth. For us, it's are they able to deal with their own, are they able to do the things that they want to be able to do with their monitoring, et cetera. So it's this interesting thing where, given if we can find that soul metric or that end user, whatever the proxy is for the end user response time, how do we trace that back to what actually happened? And I have some ideas here. And this is how we sort of scrabble up this hierarchy, in my opinion. That sort of why is it wrong? So the interesting thing here is that when we ask the question, what do we want to monitor? What do we want to alert on? We have this. We can sort of explode our data set into a multivariate, n-dimensional. I can throw in a lot of big words, but it's basically like there are a lot of. First of all, there are a lot of metrics, but also there are a lot of dimensions to each of those metrics, and they can all be sliced and diced in interesting ways. So, in other words, any individual application is running. An application happens to be running on a host, right? Some hosts have more than one application on them. Some hosts are in the cloud. Some hosts are platform as a service, and you don't even know how many applications are running on there, right? And they're in like this weird little container thing. There's this sort of nested, there's like, matryoshka doll, like sort of nested stuff, there's like nested containers of stuff, because, you have the DC, the rack, maybe they're participating in some sort of a cluster. So you have this topology of things that your applications, and therefore the metrics, the telemetry about those applications are living in. And it turns out that the way that we build things today, and more so in the future, is that there's lots of different little things that participate into the delivery of the end service. So things that participate in the delivery of the end user experience is like a lot of stuff, right? Like how many services are running on your back end? How many things have to cooperate in order for you to get a page view, right? Like how many things have to happen and like arrive at exactly the same time? And how many things can you tolerate being gone before your user starts to notice? And so very quickly we come to the realization that our data, our metrics, they live inside of a graph, right? And then this graph, it's an interesting graph because you can overlay, it's almost like SimCity, like how you can overlay the power view, the water view. Like there's all these different layers of how these things are connected to each other, and they all have different properties, right? Because there's physical connections between things. Unless you're in the cloud and it's all magic, right? But your applications are logically connected. There's literally a socket open between one thing and another thing, and they're sending data over it, hopefully. You have topologies of things cooperating in order to deliver some sort of experience to your user. And the question here is, how do we use this graph in order to provide the context, the scoping, not just for the human operator, but actually for the machine as well, because we take this computationally expensive n-dimensional problem and we can actually cut it down pretty quickly. Just by asserting relationships between things using a topology. And the really interesting thing is that if we start a feedback loop here, right? We can naturally group metrics together. We can assert relationships between things, or we can guess at relationships between things. But then the really cool thing comes in where we actually reinforce those relationships based upon the actual relatedness that we see in the data as time goes on, right? And so there's a number of different like pattern matching is like a pretty simple, like computationally simple algorithms can do basic pattern matching on a graph, and there's like dynamic time warping. There's all this interesting stuff that you can do in order to assert that these two things are related. And then the cool thing is, over a long enough period of time, you can with some pretty good confidence, you can say that hey, look, these two things are almost always in lockstep, so I think that they're related. And then we can actually strengthen and weaken the relationships between things, and we can learn the paths through your system that actually matter, right? Because if I look at the topology graph, as any of you are, as I often do for our customers when we build these topology graphs for them, when I look at your topology graph, I'm going to see a lot of stuff. Not necessarily all of it's going to be particularly relevant for any sort of critical or high path thing, right? Like, in other words, you might have a chef server which kicks up every 5 minutes and touches every machine in the cluster. That doesn't necessarily mean it's necessary for the delivery of. It doesn't necessarily mean that it's necessary for the delivery of any critical service, right? So being able to assert the relationship between things and being able to ultimately tie them all back to your end user experience is what will ultimately lead to being able to learn what are the critical parts of this graph, what are the parts of this graph that we should automatically alert on, and build and start building things against that critical graph, which is really cool. And then we can just say, if these things are highly related, when they move off of each other, perhaps that's a problem, right? That's we get a lot of things fall out of this graph model for free, if you think about it. And basically, I don't know how many people read the Dapper paper. It's a very interesting read, but once you get past the whole have to instrument all the standard libraries thing. But I mean, the interesting thing about Dapper-like systems or any sort of tracing system is that it will naturally sample down to. First of all, it's transactional, and so if you don't have a transactional system, you're screwed. But you can it traces down to like sort of a day in the life of an individual transaction. But the nice thing is that we get that same sort of graph view, that same sort of participatory view, but it's outside in rather than inside out. And what I mean by that is that it's instead of looking up from the perspective of the transaction and saying, here's all the things that touched me in order for me to be here where I am, it's more along the lines of, here's all the transactions flowing through all these systems at a given point in time, and here's where I think things are breaking on a continuous basis, which I think is a more powerful model for reacting to emerging situations. Although I'm just asserting that, so you can argue with me about it later. And so, how do we? It's very hand wavy, right? But how do we actually narrow down in and start to assert the relationships between these things and start to say, I think that this component is misbehaving, right? So the MySQL or the Redis or the whatever, why are these things misbehaving? And once we have a good idea of what are the critical paths in and out of this thing, we can start we can actually just start to build, but what I mean by models, build equations that say, hey, I think that with a given amount of throughput through this thing, this is what the output's going to be. With a given amount of load, this is what the throughput's going to be. And here's where I think it's going to taper off based upon the profile of the machine. And there's a number of different ways we can go about it. I'm not really sure which one's going to work. Universal scalability law says it gets around Q-theoretical stuff. But I mean, if you really want to get down to the nitty-gritty, you can build a lot of Q-theoretical things because computers are just lots of Qs. There's also some interesting things in the world of system dynamics. Anyone here know of system dynamics? Anybody? Yeah. It's an interesting discipline that I think, in order as a way of capturing nonlinear behavior, nonlinear dynamic behavior between components that are sort of loosely connected. I think it's a very interesting discipline that we can learn something from. And so, anyway, an aside here. So we build these models. We can set the expectations for throughput and latency. And the cool thing is that we can actually base the models on application hardware profiles. So, in other words, if I have data from enough customers, if I have data from enough different sites out there, because that's the one thing that we're all sort of missing right now, right? Is we all operate in these little silos, and we come to a conference once or twice a year. We share information, but we don't share information, right? You're not giving me your data set of performance for your critical thing. And by the way, I'm running a patched version of this anyway, right? It's there's no effort to collate all these data sets together and to actually actually be able to assert that in 99% of cases, MySQL scalability on this hardware profile looks like this. So that's what I want to build, right? And that's where we're going. And if we get a large enough data set, we can actually begin to say, not just say, we think you're in the the 90th percentile of performance for this individual component, but we can also make recommendations for hardware, right? So we can say, if you want to get the most out of this, or if this is your target, by the way, you need to buy this. That would be really cool. I think we can do it. And that actually brings us down to the whole why is it wrong when we scrabble up this hierarchy. And the real question here is what changed, right? Because that's typically what actually happens in a production, right? In a production setting, is that at some point something changes, one of your assumptions gets proven false, and then everything goes to hell, right? And the whole exercise becomes about figuring out which of your assumptions has now been violated. And I think having actual formal models that we build against individual components that live together in a graph, we can put those assumptions right up front. And then when we alert you about things, we can tell you, hey, by the way, here's the equation that I used to figure out that this is wrong, and here's all the graphs that are related to this because they all live in the same section of the graph. Oh, and by the way, here's the assumptions that went into this, and pick out the one that you think is actually wrong. And if we can surface the assumptions violated, we reduce that mean time to resolution drastically, right? And so when you wake up in the middle of the night, you actually have a human readable thing that you can say, and then even better, a human readable thing that you can rate as well, right? Because the interaction with the system is another input, and that feedback loop isn't properly captured. If you say an alert is crap, shouldn't there be something on the other end that says, okay, that alert was crap. What do I need to change about what I'm doing in order to give you a better alert? Anyway, there's a lot of high concept hand wavy stuff. We're building a lot of it, but yeah, there we go. Yeah. So but the interesting thing here is that the complexity of our systems are accelerating. We just saw this week the .cloud thing, right? Basically individual application containers, they can just move around and go wherever. This is the way forward, right? The ability to compose dynamic systems on the fly, put them together, slap a bunch of stuff together, put it into production. That's fast becoming the default way that things are built. And the big enterprises, they'll eventually catch up. But I mean, this is the transformative thing. These are the transformative things that are going on in our industry. And I know a lot of times the cloud word gets thrown around and nobody really knows what it means. But the dynamic nature of basically having a programmable data center means that we can glue together complexity much faster than we could previously, and because of that, our instrumentation has to keep up, and it's not doing it right now. So anyway, I think that data is the way forward, and we carry around our data as folklore, essentially, right? Like we're all just sort of shaking the chicken bones over a graph and saying, oh, I know what that is because I saw that 10 times before, right? But we're not collecting it, we're not quantifying it, and we're not automating it, or not nearly enough. So anyway, here's the caveats of all the crap I just said. So obviously, this is very difficult to live in a zoo of monitoring point solutions, right? Like you need vertical integration to do a lot of these things. You need that monolithic thing, which is part of what I'm trying to build. We'll see if I'm right or not. And also, you need extremely high resolution data, right? And that's the other interesting part, is that showing the change in these things. Being able to assert relationships like that, like having the high resolution data, makes it much easier to say these two things are related, because a minute is like, to a computer, a minute is like years and years and years, let alone 5 minutes. And it's like the rate of change of transactions through the system, you can't really assert any sort of relationship on a minute by minute level. Even second by second sucks, but it turns out that it's a hell of a lot better than minutely, right? And also, you can never have a thing like I'm describing can't live on premise. So, so you're all going to get sucked into the cloud one day or another. So, anywho, thank you. Feel free to yell at me later over beers, and that would be fine. Thanks.